Hi everyone, we're the Gripper team, which is Alejandro, Gustavo, Leo, and Tom. Our problem and project is to make a gripper to attach to the end of a Sawyer robot, which is the red one in the figure one you can see there. And the whole purpose of this is to act like a robotic wrist because robots like the Sawyer robot, the arms have to move a lot to have very fine movements in any degree of freedom. And our project is making a gripper to attach to the end of the Sawyer robot, which can move in all 6 degrees of freedom. So it's replicating a human wrist. Here are the deliverables, requirements, and specifications for our project. These were outlined by our sponsor, Professor Howard. The main ones I'd go over and were important throughout our project were that obviously the gripper must have movement in all 6 degrees of freedom. And we had to have the specifications we had to meet, which were very important, were translation of at least 3 centimeters in the X, Y, and Z axes, and rotation throughout those axes as well of 15 or 30 degrees. And what was very difficult was our space envelope because we had a very tight space constraint. So the diameter of the gripper had to be 8 centimeters and the height was 15 centimeters. So an early decision we had to make was what type of hexapod setup we would use. There's 4 different types: type 3.3, 3.6, 6.3, and 6.6, and they're just those different types refer to how the actuators are combined and how they're attached to the top and bottom plates. So we ran some FEA structural analysis with the same load applied to each different setup to analyze which setup had the least amount of stress. We found that type 6.6 was type 3.3 had the least amount of stress, followed by type 6.6. But because of type 6 was going to be significantly easier to manufacture because joining each actuator to each plate individually is much easier than connecting the actuators together. It ended up winning our Pew matrix, which you can see as the bottom table here, and that was the setup we decided to use in the end.
Next, what we did is to find the actuator that would work best. To do this, we looked at the data sheet of each actuators from Actuonics because we had a very small height constraint. So we needed actuators that would fit our height constraint. From the ones we found, we compare them via different factors such as the force that they could pull. And then we also took into account the ACE's recommendation, and the winner based on the Pew matrix was the L12I, which had a feedback control, which was really important for the ACE side. Next, once we had the actuators chosen and the type of structure that we will do, we perform mechanical analysis with NX, where we made the actuators move in a harmonic motion, and then we saw what the forces would be on each actuators, and we found that if you drive the platform to extreme positions, you get a lockup position, but even then the forces on the actuators were not great enough to break them, so we chose to keep moving forward with those actuators and this platform.
So after choosing the actuators, there was a lot of design iterations until we got to our final design, which is seen here. For our gripper, we decided to use 3D printing because it didn't have to support a lot of weight and it was easy to make some of the complex shapes. We chose a modular design so that each piece of the body could be 3D printed easily, and tried to fit as closely as we could around the servo we had to reduce weight and space. For the platform, starting with the base plate, we decided we needed to separate them into 2 pieces in order to make connection to the Sawyer robot smooth and easy, because it'd be a lot harder to take all the actuators and the PCB boards off from the main base plate. So that can be seen in the base view. We also rose the U-joints. We chose to go with U-joints instead of ball joints for all the actuator connections because they help limit rotation of the actuators and took up the least amount of space. But we had to rise them on risers to make room for the PCB. And then in that bottom left view, you can also see these connecting blocks we had to manufacture to keep the height as low as possible and make the connection between the U-joint and the bottom of the actuator. For the top plate, we, in order to make the U-joints work with having U-joints on both sides, we had to let them be able to rotate on their axis on either side of the platform. We chose the top plate. And to do this, you can see on the middle right picture, we used brass bushings and shoulder bolts to connect to the U-joints to the top plate so that were free to spin, but we're still locked to the top plate. And the completed device is visible on the far right. These are just a few drawings of our assemblies, one for the platform, one for the gripper, showing a little bit better exploded views of each of the components and their function.
So here we did a tolerance analysis, which will determine the manufacturing and assembly processes. So as Leo mentioned, on the top plate, we decided to use U-joints, but we decided to do the sliding fit on tolerance. So mainly what we did, we had a bushing, and we researched on like what type of screw or like what dimension of the screw would be perfect for assembly. So we decided to go with these two bushing, with the bushing and the screw that you can see in the top right. The reason of the sliding fit to reduce the chance of the lockup. And then for the bottom plate, we decided to do an interstream fit between the pins and the holes, basically.
Another important analysis we did with the fastener torque calculation, especially for the bottom screws that hold the two base plates together. They take a lot of load. And it's important that they're fastened correctly because they support the weight of the rest of the structure above them. And if they were to fail, that'd be very bad for us. So using the dimensions and the material properties of the stainless steel fasteners that we use, which are our required torque, our optimal torque came out to 1.053 Newton meters. And this just confirms how strong fasteners can be and how little torque we really need to keep everything safe and fastened without over tightening and bending the ears of our base plate too much, which could stress and eventually lead to failure. Another analysis we did was fatigue, because the device needs to be able to be used for a number of cycles and for a long time, hopefully. And our most worrisome piece were the pins of the U-joints center block, because they're quite small, but they support the weight of the entire device as it moves. So some FEA was done to determine the stress with our maximum forces that we expected on the platform, as well as our mid-range stresses for normal operation and just the weight of the platform. And using some RN factors to adjust our ultimate strength of the copper U-joint pins. The analysis for the Soderberg and modified Goodman methods satisfied infinite life, which means that no number of cycles at our expected forces should cause failure of these pins, which is good.
I'm jumping into manufacturing. There's a lot of components that we just ordered and we bought them. So as you can see in the table on the left, the actuators took a lot of our budgets. And then we also, including the screws and the bushings and all those parts that we needed for assembling the component, we also bought aluminum raw material, so we can manufacture ourselves. So as you can see in the top right, the solder interference plate and the connections block that connect the actuators and the U-joints, those were making the Hasm CNC machine. Then in the CNC prototype, we did the bottom plate and the top plate. And then for the inserts that kind of create a connection between the top of the actuator and the U-joints, we did those in the manual lathe.
So next we needed to test our devices, but because the ECE part of the team is supposed to be able to make the circuit to drive it, and we didn't have their circuit, we made our own, which is a very simple circuit with Arduinos and linear potentiometers that allows us to drive each leg individually. And this is how we drove our platform for testing.
So to actually test, we use a firearm that is here provided at the University of Rochester. So pretty much how it works is that we scan the bottom plate and the top plate. Pretty much we do 4 scans, 3 to actually create a plane, and then the 4th one to create like the flatness of those planes. So once we have those planes set, then we can start moving our wrist to the position that we desire so that we can meet those specifications. So once we scan all of the positions, we go to an X. and we measure the distance between the plane of the base axis and then the plane of those movement. So after creating all of those distances, we create this table that pretty much summarize that we pass all of our specifications, which is always great.
So as far as the future work or how we were to improve this design, there are a few improvements for design. It's mostly focused on the bottom plate. One of them being like the connection between the Sawyer plate and the bottom plate of the platform. That's because our connection is actually not fully constrained, as we learned later on, and we can improve this. We over designed it by having like 3 screws. We don't need like that many screws or that much force to hold it together. And then on the green you can see like the U joints and the pins attached to the bottom plate. But if we were to do this again, it would be good if it's only a single piece, as it would constrain the orientation of the actuators, as right now we have to adjust them by hand, which is not ideal. And then for manufacturing, if we were to remake these pieces again, we would make the bottom 2 plates together and machine them as an assembly so that the holes can perfectly line up. And if we were to make the pins for where the U joints rest, as I said before, we would just manufacture that as a whole plate. So that this is all one part and like one rigid body.
So in conclusion, well, I think a lot went well with this project, especially as we had a very small space envelope, but we still managed to hit all the specifications ourselves. And obviously we tested it ourselves, and the ECE team will make their own code to make the movement of the actuator better, but we managed to meet all the specifications with our own code. And I think because we had a lot of CAD at the start, which was in a lot of detail, the manufacturing went very quickly. We finished most of the manufacturing in just about 1 or 2 weeks. And thankfully, we were all friends before this project, and still are friends now. So it was very easy to meet together. We got along very well and divided the work very well. The key takeaways are that communication is very important, especially with the other ECE team. There's a couple of instances where there's misunderstanding and it led to losing a little bit of time. But overall, I think communication was well, and we learned that it was very important. And another thing that was very important in this project was making sure that when you agree on the specifications with your customer, that you know that you can hit those specifications, because we agreed on the specifications, and then after we did some research, we realized that one of them was not going to be possible. And thankfully, our customer let us change that specification because it wasn't too much of an issue for them. But it could potentially in other projects be an issue. And yeah, final takeaway really is that over design, you need to look out for it. We weren't really aware of it, to be honest, but with the bottom 2 plates, they were slightly over designed. So that's something to think about next time. And yeah, I guess also we could say that you want to let people who work on what they're good at, but also what they are motivated and want to learn to do. So overall, I think we all think it was a really good project, and we'd like to thank all those listed on this slide here for all their help. Thanks for listening.